Okay, we've got fresh water behind a reservoir dam. So we've got a dam of depth D. And then we've got a pipe of radius R located at a depth D. Passes through the dam. And we've got a plug firmly inserted in the pipe. Standard gravity acts vertically downward, and standard atmospheric pressure is present. Okay, so if we look at the pipe, or the pipe inside the dam here, the pressure at D is going to be atmospheric pressure plus rho GH, which is 101.325 times 10 to the 3 pascals, plus our density of water, which we're using as 1,000 kilograms per meters cubed, times our gravity, 9.8 meters per second squared, times our depth, which is given in the question as 6 meters. So that's our pressure. Now, okay, so that's our pressure at that depth from this side of the dam, but there's also pressure from this side of the dam, which is actually just going to be atmospheric pressure. So now if we look at, to get the frictional force on our plug in our pipe, we can draw a free body diagram. So we've got a force due to the water, we've got a frictional force, and we've got atmospheric pressure. So then F net is equal to the force due to the water minus our frictional force minus our atmospheric pressure, which is equal to 0 as it's not moving. Our force due to the water, so recall that force is pressure over area. Recall that pressure is force over area. So then force is pressure times area. So our F water is 160.125 pascals times our area, which is pi r squared. And our atmospheric pressure is 101.325 pascals times our area, pi r squared. So then our frictional force is Fw minus F atmosphere, which is 160.125 minus 101.325 times our pi r squared. Our r in the question is given as 2 centimeters, so 0.02 meters squared. And so our frictional force comes out to be 73.89 newtons. Okay, and now for B, it asks the total volume of water that exits the pipe during a 3-hour time interval if the plug is removed. So for this, I consider just the pipe. And now at this side of the pipe, we're going to call the kinetic energy 0. And the potential energy, just rho GH. And over here, we're going to call the potential energy 0. And the kinetic energy and then we need the kinetic energy on this side. So if we consider what did I do there? So delta U is equal to minus F delta X. Our force without our friction is just, if we look above, is just our force of our water minus our atmospheric pressure. So it's purely the it's purely just this expression. Oh, right, it's just the friction essentially, but the negative of it. So it should just be 73.89 newtons. Oh wait. Alright, I shouldn't go off script too much here. So it's just F delta X. And our force is just our pressure times our area, dx. Oh, right now I see. Okay. So our delta U is minus our pressure times our area times our dx. Our delta KE is equal to our pressure times our area times our dx then. And so our delta KE is going to be 1/2 mv squared, which is our pressure times our area times our delta X. So then if we call our mass our density times our volume, which is our density times our area times our delta X, then we can see that 1/2 mv squared is just equal to 1/2 density area delta X, and that's equal to pressure area delta X V squared. So then our V squared, you can cancel our area and our delta X. So you can see that V squared is just 2 times our pressure over our density. And our pressure is just rho GH. So it's 2 times rho GH over rho, which is just 2GH. So velocity squared for our water is just 2GH. There we go. So our kinetic energy at the output is then just 1/2 m times 2gh. So the 2's cancel, so our kinetic energy at the output is just mgh. Okay. I don't know if that's super necessary, actually, but anyway. So we can solve for a velocity that everything's traveling at as square root of 2gh, which is equal to the square root of 2 times 9.8 meters per second squared. Our height is, or h is the depth, so 6.0 meters, which is 10.84 meters per second squared. So our change in volume we used as our area times our dx. So our change in volume with time is our area times dx by dt. So our velocity is our dx by dt. So this is pi times 0.02 meters squared times our velocity, which is 10.84 meters per second. And so then this is 0.0136 meters cubed per second times 3 hours. So we need to know, so I'll leave that actually. So now if we want to know how long it is for 3 hours, then we take our dv by dt and multiply by our delta time. So 0.0136 meters cubed per second times 3 hours times 3,600 seconds per hour. And so that comes to 147.2 meters cubed. So our volume our total volume is 147.2 meters. 147.2 meters cubed over 3 hours. Okay. All right. So checking to the solution here. So we get our frictional force is 73.9 newtons, so that looks good. We can set v squared to 2gh and solve for our total volume as 147.2. What? Okay, 147 is what they gave at the bottom, and 143, so that must be just a mistake. So that looks good.